Hi, this is Larry. This is day 20 of the 30-day Leetcode challenge. I'm going to solve this problem to you live. I haven't seen it today, but let's go. Construct binary search tree from preorder traversal. Return that the root node of the binary search tree matches a given preorder traversal. We call that the binary search tree is the binary tree of every node. Okay, I mean that's a binary search tree. Okay. Okay, that seems pretty. It could be any preorder. Like it doesn't have to be. Oh, this is the given preorder. Okay. That seems, I mean, so it seems like a good test of your CS fundamentals. I don't think there's anything tricky about it. I imagine I'm going to do something like a um, just recursive function, and then it will take care of itself, hopefully. I think that's what I'm going to do. And while you're watching, feel free to hit the like button, hit the subscribe button, leave a comment. Let me know how you feel about today's problem. Okay, and n is less than 100. The values of preorders is distinct, so there's no ambiguity. Okay, so what does the preorder mean, right? When you first look at the first item, so the first item is 8. That means that is the preorder. So that means that's always the first node you're going to see is always going to be root, and then everything that's smaller than it will be on the left, and everything that's bigger than it will be on its right. By definition, because it is a binary search tree. So from that, we can recursively construct. We can recursively construct pretty much everything, right? Yeah, and there's a little bit of. So I think right now I'm just thinking about complexity. Because let's say you're magically given this middle point, then you can do it very quickly. But if you're not, then you actually have to do a linear scan to find out that where the first point is, right? So from that case, well, I'm also thinking a little bit of like, can I do binary search? I suppose you can. But given that, well, so there are a number of nuances that I would think about in terms of just optimizing the complexity on an interview. These are the things I would talk about. But let's get one version of the code down first. And given that n is equals to 100, and if this is a competitive programming contest, I'll definitely just not care about n squared, right? So let's do that first, and then we'll talk about how to optimize it and how to change the code a little bit to make it better, and so forth. Okay. So now we have an algorithm. We will take the first item and then kind of partition the left and the right. So you could, like I said, because all the values are distinct, you can actually find this midpoint by binary search. And then we could kind of talk about complexity of each one. Okay, so root is equal to tree node of preorder item. Well, let's check that preorder is if preorder is 0, then just return none, maybe. I don't actually know what the expected value. Okay, I mean it's more than 1, but maybe that's actually a good signal value because okay. Yeah, okay. So then now let's just go through the array for let's just do n is equal to length of preorder, and we're going to do a little bit. I mean, right now our focus is to get it correct, but there is going to be a little bit hand wavy stuff here with respect to creating things that are on the stack and so forth, if that makes sense. And what that means is that we're going to use space very liberally because n is up to 100. But we'll talk about what are the results of us implementing it the way that we have, and how we could go about attacking it and making it better, and yeah, just a little bit, just a little bit better in terms of performance in multiple ways and optimization and stuff like this. But again, n squared should be good enough to pass. But for an interview, you're probably gonna these other things will come up because, especially if you solve it too quickly, there's a lot of time left. But yeah, but so right now let's look for the first index um, in which uh, it is bigger than the root node. If this is bigger, then we can just, well, that means from this index plus all the way to the end uh, elements will be on the right, right? So let's do that. Let's break afterwards, or maybe even return. Let's just return that because I don't think we need anything else. We should return root, but also else return root as a base case. Yeah, okay. So now, well, actually, no, this is not true. That means all the nodes are on, all the nodes are smaller than root node. So we actually have to do something. So I was a little bit hasty there. But now let's do root dot left is equal to tree, oh, sorry, is equal to self.bst from preorder, and this is the recursive part of the function. Preorder, we want this, so the left will be from 1 all the way to index -1 inclusive, right? So that's what we want. With that right is good. And now we have the base case node here will return none, so we don't have to we don't have to do any checks as a result. And then here is just index all the way to the end. And then that's it. And then here all the nodes are smaller than root node. So let's just do this. And then let's test some test cases and then see. I mean, this is not. Oops. 917. Did I make a mistake somewhere? Oh, why did I go all the way to n-1? Because I wanted to collect n, but whoopsie. Okay, so this is mostly right, but as you can see, there's an edge case that is missing, which is something that, so I definitely have an off by one. That's why I wanted to go to n all the way, but does this, I might have my syntax a little bit wrong on a Python. Okay. So something about with Python and indexing is that I always don't know if it is inclusive or exclusive. So I got yeah. But that's what some in practice will kind of allow you to not make that kind of mistake. But that's okay. Yeah. So now let's test a few more cases. But it's good that this one is it starts off strong. Let's say everything's on the left. Let's say everything's on the right. Okay, so I mean, this looks mostly okay. So there probably are a few more edge cases. Let's just do, I don't know. And then maybe just 1, 2, 3, 4. But I don't know if there are any more edge cases per se. I would also say that, that's what I would allocate getting a good, strong fundamentals is that even if you make silly mistakes involved by 1, that's fine, right? Like that didn't cost me that much time. But if you don't know the algorithm, then it will take you the entire time. That said, let me get it correct first. Okay, cool, accept it. So yeah, so that was not a bad problem. Pretty straightforward. It does test both recursion and a little bit knowledge about the binary search tree and what a preorder traversal means. Definitely, I might have hand-waved a little bit over it in how to interpret it. And there's some like assumptions that I probably skipped over a little bit, to be honest, because from my experience. I'm just like, oh, these are things that I know to be true, but I don't even know to articulate it because they're so innate in me. So for that, I apologize. Definitely leave a questions if you have any doubt and so forth. Let's talk complexity real quick, right? So the way that I implement this will be n squared. Will it be? I mean, okay. I mean, it'll. I mean, I think okay. A really easy way to analyze this would be that it's O of n squared, which is as an upper bound, which is technically true. But can we get a tighter bound? And that's what I'm trying to figure out a little bit. Because for every time, let's say all your things are divided in the middle, and the way that I did it, you have to look at half the element. So the recurrence is all. So if you want to think about recurrence with things, then you have t of n is equal to t of n over is 2 times t of n over 2 plus O of n, which is actually like n log n, right? So I think this is n log n as a result. But can you do better? So there are a couple of things we can do better. This is n log n in terms of runtime, but there's space as well, right? And the space is, well, we do have a pointer to slices every step of the way, and this can be on the stack space of n of them at most, especially on the in the degenerate case of everything is a linked list. So yeah, so definitely the O of n space, which maybe you can't do that much better, at least in terms of the big O of n, because you're allocating O of n items anyway for each of the items for the O of n, because there's a tree node for every item, so that's going to be O of n anyway. So it might not be worth doing better, but it's still nice to try to do a little bit better. And in this case, that one is really easy, right? Like, well, maybe just don't do slice. Put this in a lookup thing somewhere, and then just reference it only once, and that's a pretty standard thing. So then you don't have to. You still will deal with stack space, and for that, you're doing O of 1 on the stack, and there's O of n stack depth at worst. So that's it's still gonna be O of n, but at least that's slightly better than allocating all these objects where in theory it can get big. In terms of performance, as we said, we know that in a way, 8 being in the front means that it is actually a pivot on the remaining data. So even though this is not you think about binary search or repeated doubling and so forth. One thing you might look for is, well, is this monotonically increasing or monotonically decreasing? Because in that case, it's very easy to see why you can binary search, because it'll get either it'll get smaller, so then it gets better. But actually, because your first node serves as a pivot for the rest of the thing that you're processing, you can think about the function is a Boolean function of, is this element bigger than the pivot element, which is kind of what I do here, right? So if you look at this function and then look at the data, the input parameter, given that it is a preorder traversal, this actually function goes from false, and then true, and then true, all the way through, right? So from that, you can actually binary search, right? So then now our recurrence function, which before we said was O of n is equal to 2 times n over 2 plus O of n. Now you could actually get that to t of n is equal to 2 times t of n over 2 plus log O of log of n, right? So what does that recurrence solve to? You can use the master theorem. There's a couple of ways to solve that. I'll leave it as a practice for the viewers at home. Leave a comment. I'll give you props and respect if you do get it very quickly. But that's how I would analyze and how I would try to optimize for this problem. Overall, already basically this problem is a very fundamentally focused problem. It's focused on your fundamentals. And as an interviewer, like I think it is a reasonable problem. It's it's annoying enough. It's a little bit tricky, but not too tricky. Maybe I would throw a little bit of a twist to it, just because this particular problem is well studied. People practice it all the time, but because they know that it might have a good possibility of being asked. But for the metagaming aside or meta interviewing aside, it's a good problem. I would recommend practicing it, and because you might not get this particular problem, but you'll get problem that builds on this problem, which is something you should practice about. But yeah, overall an interesting problem, not a bad problem. Tree problems are uh, always going to be a thing, if anything, because recursion is a skill that everyone just appreciates, and tree bombs has a very recursive structure, and yeah. So that's all I have for this problem. Let me know how you think. Hit the like button, hit the subscribe button, leave a comment. Let me know how you did and how you like this problem. And I will see you tomorrow for hopefully the new problem. See ya.